afternoon, everybody. This is the post-lunch talk. So I see everybody's still kind of digesting, no problem. This is a very easy talk. My name is Giuseppe. I work for KDAB or KDAB, or the guys in the suits, or the beer experts. Make up your own joke. Today I want to talk to you a little bit about how do we optimize the rendering of Qt 2 applications. This is a topic which is close to my heart, being a guy that plays with graphics a lot, but also one element which is somehow somewhere forgotten when we build Qt 2 applications. Qt 2 applications are very easy to build, it's very easy to get something nice on the screen, and sometimes that very nice design ends up being also in the final product, and almost in very few cases, people stop midway through and start asking themselves, is the thing that I'm putting on the screen actually efficiently rendered or not? And this is important. This is important because the UIs we're building with Qt are fancy UIs, dynamic UIs. We want them to run at 60 frames per second all the time. And if we do some mistakes in the way these applications are rendered, then we will not achieve that, or we'll burn a lot of CPU and GPU in the process. And I believe that's a bad idea. So, few words about me. So, who am I? I come from KDAB again. I'm a trainer. I gave an OpenGL training a couple days ago, but I'm also a developer. So, I use all the things I'm about to tell you about. I've been using Qt for a very, very long time, back to around 2000. I am a Qt contributor. I'm a Qt approver. And please, I talk with anybody about anything. But if you want to talk about Qt, so ask me about something about Qt Core, Qt Quick, Qt GUI, C++, 3D graphics. I'm in that area, right? Okay. So what are we going to talk about today? Today we're going to talk about performance in Qt Quick. And when I talk about performance in Qt Quick, of course, there are many, many aspects, many, many angles. Other talks at this very conference are going to talk about some of the other angles that we're not about to talk here. So performance, what does it mean? Well, we could mean something like CPU performance or C++ performance, right? Is our application efficient? Is it using the right algorithms to solve the problem? How about the I/O this application is doing? Is it blocking everything because it's opening a gigantic file, etc.? Maybe our application is multi-threaded. Is it using multiple threads efficiently? We are not going to talk about that. Qt Quick comes with a JavaScript engine. And in big applications, I've seen this engine being pushed quite to the limit. People writing thousands, if not hundreds of thousands of lines of JavaScript. And of course, there is optimizations that are possible in there. There are better ways of doing certain things. We're not going to talk about that. And then there's the last thing, which is about rendering performance. That is how our application is actually drawn on the screen, right? This is a very big topic because it touches many, 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 many points. The things we're going to see today are about the runtime performance of our application when our application is using OpenGL. Now, if you attended Laszlo's talk yesterday, you should know, or Lars' keynote yesterday as well, you should know that Qt Quick is kind of moving away from OpenGL from a certain grade, in the sense that it's also embracing other 3D APIs, such as Vulkan, such as Direct 3D. So I should probably remove that sentence from there, because actually all the advice I'm going to give you here applies whenever you're using a 3D graphics API, okay? On the other hand, if you're using the software renderer, then most of the things I'm going to tell you about don't quite apply in the same way, but still there are things that you should look for when you design your application, okay? So what do we mean when I say performance in rendering something, right? There are many, many, again, things to talk about, but typically if you talk about performance and we talk about rendering, I mean that we need to draw things faster. And there are several ways to achieve that. This is graphics, and in graphics, any cheat is good, as long as the visual result is the same. So what we could do, we could, in order to draw faster, we could draw the same things that we're seeing on the screen in a more optimized way, and we're going to see a couple of those. So draw the same things, simply less time. Sometimes we may decide to simply draw fewer things, and therefore being more efficient in that direction. Some other times, we may decide to draw simpler things. I mean, do I really need to load a 4K background on this device, which has a 200 by 100 pixel screen? Makes no sense, right? Let me just load a low resolution asset and draw that asset instead, because the user cannot tell the difference. And finally, in some other scenario, we may decide to apply, for instance, trade memory for more speed, to apply caching more aggressively. Okay, that's the typical kind of trade-off we have there. So that's one area, draw things faster. Another area is to use less resources. And typically, when it comes to Qt Quick, the resource that we're going to abuse is memory. Again, it's so easy in Qt Quick. Let me just load this nice background. It's a 4K PNG. And that thing over there is just about to eat several megabytes of very precious VRAM, of which it is scarce on my phone or my embedded device. Finally, there are some other concerns. For reasons of time, I cannot talk about them in this talk, but things like improve your battery consumption, improve your power. If you're targeting mobile or if your embedded device is without a power source and it has just its own battery, then how to improve that. And also things like reduce the latency of the drawing, right? There is, due to technological reasons, a latency between the moment you say draw that and the moment that appears on the screen. Usually it's a few milliseconds and nobody can tell the difference. But what if those few milliseconds are too many for your use case? Then, of course, there are techniques to address that. But again, we don't have time today. So the rest of the talks looks like this. I'm going to give you a series of recipes, like one-shot recipes about things that are typically going wrong in many applications and how to fix them, or how at least to detect them. I know I'm doing something wrong and I should fix it. And then perhaps the solution that you're going to use is different from the one I propose. So number one, let's detect and avoid overdraw. What do I mean by that? What is overdraw? The concept that we're trying to address here is this. The easiest way to draw faster is simply to draw less. Let's make Qt Quick not to draw things that I cannot see. Which, if you think about that, makes sense, right? If I got an element in my Qt Quick scene and I cannot see it, why should I draw it in the first place? That's just wasted CPU power and GPU power, right? So in the ideal case, what we would like to do is to have Qt Quick draw each and every element and all and only the elements that the user can see. That is not what Qt Quick does. Qt Quick actually, what it does is to draw a superset of that. Qt Quick is going to draw all the elements that are visible, that is, have the visible property set to true. And this includes elements that are, for instance, are out of bounds. You simply move them out of the screen, and now you've got an element sitting somewhere off screen that you cannot possibly see, but Qt Quick goes there and draws it. Items that are completely obscured by opaque elements on top. So maybe you got some transition in your application, you got a screen that covers the main screen. The main screen behind is still there, and if it's got visible set to true, it's still being drawn. And other things like items that are clipped. Yeah, if you got an item which is clipping its children that are outside the parent's geometry get clipped, but they get drawn nonetheless. So we should try to address these issues. We should try to avoid drawing things that you cannot see in the first place. And the thing about Qt Quick is this, is that Qt Quick itself, although it could in principle, but it does not implement any of the optimizations that are possible to detect this case and not do overdrawing. In particular, it does not employ any technique such as a Z-fill pass or frustum culling or collision culling or any fancy technique. There is a reason for that. And the reason is maybe doing one of these techniques is more expensive than just drawing everything in the first place. But that's just a maybe. Some other cases, actually, that's not true. So we should actually go around manually, find all the elements that are expensive to draw and are not visible, and set them their visible property to false. That's our job as developers. Okay, we cannot just say, look, this element, I moved it off screen, user can't see that, that's fine. Well, it's not so fine. Qt Quick is still seeing that element, is still rendering it. Yeah. Using some built-in elements helps in this regard, because of course the built-in elements like stack view and similar do the right thing for you. But sometimes you are just developing your own custom component or your custom visualization, and you may just forget to do this. Okay, so how do I detect if my application is actually falling into one of these traps? The simplest way possible is run your application inside Gamma Ray. How many of you, survey, know about Gamma Ray? Raise your hands, please. Okay, I still see some hands that are not raised, and that's bad because there is this awesome tool which is absolutely for free. Just go on GitHub, download it, and use it. It's called Gamma Ray. I'm going to use it in a second. And what this tool can do for you is give you this kind of insights inside your Qt application. Gamma Ray is a very comprehensive tool, and amongst its functionalities, there is overdraw detection. This is actually not implemented by Gamma Ray itself. It's a built-in inside Qt Quick, and you could achieve the same by exporting that environment variable right there. But nonetheless, Gamma Ray makes it much, much easier because you don't need to restart your application under a different environment. You can just connect your application to Gamma Ray and switch overdraw visualization on and off. Or if you don't want to use Gamma Ray or you cannot use Gamma Ray for any reason, try and use some OpenGL logger and look for these numbers. There are numbers that any good profiler will tell you about overdraw ratio, Z complexity, number of called primitives, and so on. Okay, look for those numbers. If those numbers are high, then you know that you're doing overdraw and you should stop doing it. So is there a small, yes, example coming up? Just to see some code, right? So I've built a very small example here. Just it's, if you want, the super simplified version of what could possibly go wrong. This is my application. Beautiful, quick application, okay? But please do a little exercise for me. Imagine you got some content in there, okay? And any moment in time, the user can click in there to open a side menu, okay? So there is a side menu. Yep, it slides in from the side, and it goes away when you click somewhere. Sounds good? Now, okay, I got that side menu sliding in from the right, but also I think that user may get distracted by what's already on the screen. So I want to hide the main content with another opaque pane, like a black image or something, so that user can focus on that right side. And if you notice carefully, yeah, the background of the main changes. And that's simply implemented by having another element covering the background. Okay, so this application, as simple as it is doing overdrawing. Okay, in particular, the right menu moves out of the screen, but I never hide it. I just forget to set visible to false. Okay, and also when the pane that blocks the main view of the application appears, I should set the thing behind it not visible, right? Because now there is something in the background completely hidden, but I still am not doing that because I implemented all of this by hand instead of using, again, stack view or similar better techniques. So how do I detect that that's even happening, right? I can just launch Gamma Ray very easily. I've got a shortcut for this inside Creator. And I think it's this thing right here. Yes. Okay, sorry, disable that. So this is Gamma Ray. It's, I'm not going in explanation of the tool, but I want to show you what the tool can do for you. This is Gamma Ray, and this is running attached to the application. This is a preview of the running application, which is still running over there, right? And if I manipulate the application, you see the preview changing as well. Okay, and inside Gamma Ray, there's a little button that can enable this overdraw visualization. And it's this button right here, I believe. This one? No, sorry, it's this one. Yeah. And look at the application running, and the visualization in the application changes drastically, showing, if you want, a 3D composition of the scene, if you want, level by level. So what I got here is that I got the background, that blue background that was in the middle, the text on top of the background, and you can see there is something on the side which is completely outside the screen. You see that part of the right? Yeah, that's my menu. It's sitting outside the screen. And it's visible, and Qt Quick is rendering it. Okay. Now, maybe that menu contains hundreds and hundreds of entries or something like that. That's expensive work for your GPU to do when it's not visible. You should set the menu visible to false when it's outside the screen. I can bring the menu in. So I can click, the menu goes in, and if I look now at the composition of my scene, now I see that there is still something wrong, in the sense that there is a background, and then there is a layer which completely obscures the background, because I don't want the user to be distracted, and then there is also the menu on top. I hope you can see that from back there. Otherwise, please run this example on your laptop, and you can see that as well, right? So what I'm doing wrong here is that I got one layer completely obscuring the back layer, and the back layer is still visible and is still being rendered. Yep. And if there is something expensive in there, some fancy shader effect or whatever, I may still be paying for the price of that rendering, even though I'm throwing all the content away. So this is how we probably detect overdrawing. And of course, the fix, well, depends on what you're doing. But for in this case, it would be to hide this menu when it gets moved out and hide the background when the foreground appears. I need to set manually visible to false inside my source code for this to happen. Sounds good? Okay. So let me close this. Let's move to the second point of today's presentation, which is about caching. Consider caching all the elements which are expensive to render. Okay, sounds good. What do I mean by that? What is expensive to render? And what is caching specifically? So caching means what you think it means. It's the typical space for speed trade-off. In the context of Qt Quick 2, caching means trading a little bit of video memory, okay, in exchange for rendering speed. That happens, practically speaking, if you want, by taking a screenshot, double quote screenshot, of the elements that are expensive to render, okay? And next time I need to render them, I don't actually render them, I just simply use the screenshot I had in the past. Yeah, and that's super cheap. So this is extremely useful to apply in case we have some expensive element on the scene. The usual suspects are things like shader effects that designers love, because designers love to put, oh, got nice icon, let me put a drop shadow, maybe some blur around it, and so on and so on and so on. And these things have a cost associated with them, right? A cost that we may actually pay every single frame. Why is that, though? The reason now has to do with the fact that we are using this kind of 3D programming APIs. An API like OpenGL and pretty much any other 3D API does not support something called partial updates. What does that mean? It means that every time anything at all changes in our scene, our rendering code or Qt Quick renders code has to, first and foremost, clear the entire screen, and second, to redraw everything from scratch. That's how these APIs work. So let's accept that as a fact of life. Where's the catch? The catch is I may get something on the screen which is expensive to render, and that's something that has not changed at all since the previous frame, yet I have to redraw it from scratch because that's how OpenGL works. Yeah, because I need to discard the previous contents and redraw it. So I may have something very complicated, a very fancy, again, shader effect in the middle of my screen, and then perhaps in one corner, I got a blinking icon telling me to do something, and that single blinking icon causes the entire screen to be refreshed. Yep. Yeah, Lasso is saying, yeah, I know. Yeah, that happens. Okay. So how do we figure this one out? This is slightly more complex because this requires a definition of something which is expensive to render. It is not trivial to figure out what exactly is expensive and how much is expensive. The best suggestion I have for you is run your application inside a profiler, such as Nsight or CodeXL or API Trace or your favorite OpenGL profiler, and then ask that tool to give you a frame breakdown to know which calls are expensive. And then you will know, okay, drawing that particular element on the screen took 1,000 OpenGL calls. That sounds expensive. I should probably think about caching it. And as usual, shader effects are good candidates for this because shader effects are expensive to render. Yeah, doing a blur step is several steps and so on. Okay. So suppose that then I identify an element which is expensive to render. How can I tell Qt Quick, please cache the contents of that element? There is a way for doing that, and the name of that is not some caching property, but it's a very mysterious property. The simplest way is to set that property called layer.enabled to true. Okay, it exists, trust me, and you can simply set that to true. What that property does, again, is to tell Qt Quick, please take a screenshot of my element and save it in video memory. Okay, the next time you need to redraw that element, copy and paste from the screenshot. Do not redraw the element from scratch. And that may be much, much cheaper than actually redrawing the element. Okay. Of course, if the element itself changes, so it needs to be actually redrawn, Qt automatically discards the screenshot, redraws the elements, and takes another screenshot. Yeah. So it's all automatic for us, and we don't have to do anything. Okay. So what's the cost of this? More video memory usage. And for that reason, it actually makes sense to cache bigger elements rather than smaller elements. What do I mean by that? Well, again, suppose that I got, I don't know, a toolbar which has got 10 buttons, and each and every button is expensive to render. It will probably make more sense to cache the entire toolbar rather than having 10 separate caches, one for each button. Yeah, there is a trade-off involved there. You need to find out which one is the best for you. So I got an example for this too. If I can find creator, here we go. So this example is, yeah, here we go. This example is a very small example. I should probably reduce the size of this screen. Yeah, sounds better. So what's happening here? What's happening here is that I got some text over there, 3 different texts, over which I've applied several blurs to make them look cool. Okay. And that text does not move at all. It's there, it's static. But somewhere else in my UI, there's that small rotating thing. You see that? Now, that small rotating thing is causing the entire screen to be redrawn from scratch, including reapplying n times the blur over there. Okay, so that's, generally speaking, very expensive. The simple solution would be to cache those text elements. And now, again, I can decide. I could cache element by element, so I have 3 caches, or I could decide to cache the whole thing, because I see that, look, the entire thing is expensive. I don't need to cache them individually because they're not going to change. And the way to do so, if I can find this example, yeah, it's here. Yeah, it's already prepared because I prepared, is find the element which contains this text with the shader effects, etc., and set that special property called layer.enabled to true. So I can then save this and launch it again, and that's it. The visual result is identical. Okay, but now at every frame, what happens is that the element on the bottom gets redrawn because it's different, but the element above, since it does not have, since it's not being changed in the meanwhile, simply gets copy and pasted from this screenshot. Okay, so I'm saving a lot of GPU power. The trade-off is more GPU memory utilization. Okay. Now, before I can go forward with my next suggestion, I need to do like a little sidetrack and make this a little educational moment about understanding OpenGL and understanding the performance of OpenGL. I need to do that in order for the next point to make sense. So I'll do this little sidetrack. Please stay with me for the next 3 minutes, and then we'll see another advice. Okay. What do I mean by understand OpenGL? Qt itself is rendered today on majority of cases using OpenGL, but as I said at the beginning, this will not change in the future, even with Vulkan, even with Direct3D. So these suggestions will apply even then. So first and foremost, what is OpenGL? What is OpenGL all about? OpenGL is a pre-specification. It specifies an API for doing 3D graphics programming. Qt and OpenGL always have went quite well hand in hand, because OpenGL is cross-platform, Qt is cross-platform. A few years ago, a bet was made that OpenGL was going to be ubiquitous. That bet has not quite paid off, but yet, indeed, these days, whatever device you find, it has OpenGL on top of it. So you can use it to access that device's GPU. OpenGL has a very, very long history. Okay, it comes from the 80s, and then in the middle, until these days, a couple of paradigm shifts, so a couple of reboots have happened in the middle. And today we used to use something called modern OpenGL, but that's another story. So what is OpenGL all about? You may have seen this picture all over the internet. I'm not going through it. OpenGL is all about defining the behavior of a so-called data flow processing pipeline. What is a data flow pipeline? It's a series of steps. You put data on the top, and this data gets manipulated through these steps until you see something on the screen. That's the 3 seconds explanation about what OpenGL is all about. Okay. I'm not going through those steps. That's not really important. The important part is that you put data on the top. Yeah, this data flows through the pipeline, and you get pixels on the screen. Now, what happens inside that pipeline? Yeah, got bigger picture again. What happens in order to use that pipeline is something which is really, really important to understand. In order to use that pipeline, OpenGL, at least modern OpenGL, requires us to set up a lot of state upfront. What do I mean by that? I mean that before we can actually tell OpenGL, please draw something, we need to set up a lot of state around it so that the OpenGL machinery is happy. In particular, we have to set up things like the inputs of the pipeline, and these inputs have special forms, usually are something called vertex buffer objects. We have actually to tell OpenGL what certain steps in that pipeline should do. There are a few steps that actually are there, but they're empty boxes, and we have to fill them in. Things like the vertex shader or the fragment shader that you may have heard of are by default empty boxes. You must fill them before you can actually tell OpenGL to draw. You may have some extra data. You may have uniforms, you have textures that you need to set. Yep. Plus endless extra switches and knobs to control the behavior of the pipeline. Things like, do I need to do face sculling or I don't? Do I need to do depth testing or I don't? Yep, there's a few hundreds probably of these knobs that allow us to control the behavior of the pipeline. Moral story, summary. Only after everything is set up, we can actually draw something. Yep, this all setup mechanism is quite expensive and quite boring, to be honest, but we have to do it. And after that, we can start issuing draw commands. Yep. Now, when we tell OpenGL, please draw something, what happens is that OpenGL looks at the current configuration of the pipeline and uses that configuration. Yep. And that configuration never changes while OpenGL is drawing. Yep. OpenGL draws something according to the current configuration and the current configuration only. Which means this: if I have to draw different things that require different configurations, what we have to do is you set up all the state that you need, right? You tell OpenGL to draw something using that state, and then you have to go back to step one, set a different state for drawing something else, and then draw that something else. For instance, if you got two different objects on the screen, and each object has its own vertex buffer object, as its own geometry, you draw the first, then you switch the buffer, and then you draw the second. Yep. So you have to stop the drawing process in the middle in order to switch state. And to read this the other way around, you cannot draw different things together if they require different state. Yep, that's the way to read this. Okay. Now, this machinery is extremely complex. How can we understand how to make it go fast? It's hard to understand. So for that reason, I always use this analogy during my trainings. There's a little analogy about that I found works quite well in order to understand OpenGL performance. And I like to make this kind of similarity between OpenGL itself and a high-speed train. Okay, that's an Italian high-speed train. It's the ATR 1000, goes over 400 kilometers an hour. It's quite a fast machine. And why do I say that this thing is similar to OpenGL? Well, let's see. What is a high-speed train all about? Well, it's about going fast and transporting hundreds of people at very high speeds. Yeah. What is OpenGL all about? Well, it's about fastly drawing hundreds of thousands of geometric primitives per second. That's why we're using it. Okay. Now that's good news. What is not so good news? Well, I mean, it's not that trains can run anywhere now, can they? I wish they could, but high-speed trains only run on certain places. They run on tracks, and you must lay down tracks before you can have a train running on them, right? The same story is similar to OpenGL. OpenGL cannot just draw anything you want. OpenGL only understands something, triangles pretty much, and nothing else, right? And before you can draw anything, as we just discussed, you need to set up a lot of state in advance. You cannot go there and tell OpenGL, just draw something. No, it doesn't work that way anymore. You need to tell me exactly where this data is, in which buffer it is, all the textures, and so on. And then you can draw. And for the not so good news, trains, high-speed trains, have a lot of inertia, or momentum, to be more accurate, okay? In particular, they take forever to speed up and slow down, and that's the reason why high-speed trains don't stop every 5 minutes. right? They only stop in major cities when they travel between them. Because stopping high-speed train very often is a super bad idea. They don't work that way. And the same can be told about OpenGL and GPUs. GPUs have a lot of inertias, double quote inertia, okay? Because they are complicated to set up, because in the general case, they are far away from your CPU. So you need to talk to them, and there is a latency involved in this talk to them, which means stopping the OpenGL pipeline too often is a bad idea. You should never stop it very often. Okay, the ideal scenario for OpenGL is to have a lot of data to process, and then you let it go. Okay. However, we have just seen that that is not the case. Why is not the case? Well, because we have to stop every single time we have to change a part of the OpenGL state. Every time we have to change anything in its state, we have to stop the pipeline, switch state, restart the pipeline. Okay? And this includes anything. For instance, which object do I need to render? If these objects are sitting in different buffers, you must draw an object, change the buffer, draw the second object. Which textures are bound? If you need to draw the same object with two different textures, set the first texture, draw the first one, switch texture, draw the second one. Opacity settings, clipping settings, shaders used, render target if you're drawing on screen and off screen. Okay, any single change of this requires you to stop the pipeline and restart, and having too many changes is bad for performance. Okay, so how can we do this in a better way? Well, in the ideal scenario, in the fantastic world, what we would try to do is to set up OpenGL in a way that it's able to draw as much as possible with as few state changes as possible. Okay, and if you're wondering what modern OpenGL is all about, it's all about this. A series of techniques added in OpenGL 3, OpenGL 4, and now in Vulkan are all about doing this in an efficient way. Things like instance-set drawing, UBOs, SSBOs, texture arrays, binderless texturing, indirect drawing. They're all about giving OpenGL a way to draw as much content as possible on the screen in one go, because you don't have to ask it to stop. Achieving this is easy if you're building your own game engine or something like that. Well, not so easy, but it's possible. But Qt Quick is too much general, right? It cannot assume anything about how you're drawing your application, and as such, it cannot employ most of these features and in a sensible way. And from another point of view, Qt Quick itself, the renderer, is actually at the moment kind of bound to only what it finds in OpenGL ES2. And OpenGL ES2 is a very old API. It does not actually support any of that. Okay, so in order to be as much compatible as possible, Qt Quick does not more or less deliberately implement many of these techniques. But it does implement something, though, and that's the important part. That is, it does implement a form of state change minimization that we should try to exploit inside Qt Quick. So that was the theory. Now let's see the other advice. How to minimize state changes in Qt Quick. We've just seen why that's important. Let's see how to do that. So Qt Quick renders a given scene using OpenGL. Okay, we know that. However, how does it do that exactly is very interesting. The way Qt Quick renders a scene, maybe you got a rectangle, a text, an image, is not by walking through the element tree and asking, please image, draw yourself, please text, draw yourself, please rectangle, draw yourself. That will be suicidal because it's super expensive to keep switching state between elements. So the mapping between elements in a scene and OpenGL calls is not one-to-one, because that would issue lots of draw commands. Qt Quick does something much, much smarter. What Qt Quick does is, before rendering, is building a data structure that goes under the name of scene graph. Now, scene graph is a buzzword in the computer industry, in the computer graphics industry at least. It means anything. In the case of Qt Quick, that's a dedicated data structure. And this data structure contains all the information that Qt Quick needs in order to render a given scene. Okay? So all the visual representation of the elements in your scene gets gathered by the Qt Quick rendered and stored into this ancillary data structure. Okay? So the scene graph contains very, if you want, a low-level description of your elements. Okay? If you have a button The scene graph does not care that you can click on the button, how the button reacts to user inputs and stuff like that. Only the information that is necessary to rendering. Okay, that typically means triangles, so the geometry of the button, if it's got an icon on top, a texture for that icon, stuff like that. Very low-level stuff. Okay. And by the way, you can actually use a tool like Gamma Ray to visualize the contents of a scene graph. I've taken a screenshot here to make it simpler for me to not navigate inside Gamma Ray. So what's happening here is that I got this particular element selected. That's a rounded rectangle inside the scene. And if you navigate into Gamma Ray panels, you can find the scene graph visualizer. And for instance, we can visualize the geometry of that particular element. And that geometry is made of this kind of representation, which you can see it's a bunch of triangles. Okay, it's faking the roundness by having enough vertices down here. And these are close enough that are 1 pixel on the screen, so you then cannot see the difference. And there is also anti-aliasing employed, and that's get employed by having a 1 pixel thick border to make it fade to transparency, so you think the border is smooth. Yep, that's what we do in graphics. We cheat a lot. Right? We don't actually have anti-aliasing in the hardware, we fake it like this. But anyhow, this data structure exists, and it's used by the renderer to gather, if you want, a scene-wide knowledge about how a scene needs to be rendered. Let me be more accurate about that. The Qt-Quick renderer, what it can do is that it can transverse this data structure and try to find the optimal way to render a given scene. And the optimal way is almost never render each element in order, but let's do some extra optimization of this data structure. For instance, suppose that we have a scene that looks like that thing on the left. That scene contains a rectangle, red, okay, some text in green, and another rectangle which is rotated in blue. That's my scene. That's what I code in QML by putting rectangle, text, image, and so on. Behind the scenes, this particular element tree becomes part of this scene graph data structure. And inside the data structure, there are a few interesting stuff. So for instance, for each rectangle, I got some geometry, I guess 2 triangles for describing the rectangle, a material that tells how this rectangle is filled. So that's a solid fill with red, I guess. The text also contains some geometry. It contains a different material, typically a different shader in order to draw the text, and possibly a set of textures, because each and every letter, each and every glyph, to be more accurate, typically is part of some texture and needs to be rendered coming from that texture. And down there, I got a rotated rectangle. So that one contains some geometry, some material, well, actually the same material of the other one. They're both drawn the same way. And also a transformation applied to it because it's slightly rotated, right? So this is what the scene graph contains at this point. What the renderer can do is analyze this data and figure out, wait a minute, both rectangles are rendered using the same shader, okay? So what I can do is that I can set that shader, set that part of this OpenGL state, and draw both rectangles first. Yeah, without switching state in between, because it's the same shader. So I can draw both rectangles, and if I'm even more clever, I can merge the geometries of the 2 rectangles in one bigger geometry, 4 triangles, right? And draw them all in one call, not even 2 calls. Why not, right? Why stopping there? Then I got my 2 rectangles on the screen. Then I switch shader to the text shader, and I draw the text, okay? So this thing does the optimal number of draw calls and, well, the optimal, does a much better job at drawing less and switching state as few times as possible, okay? So this mechanism is called batching inside the Qt-Quick engine, okay? So in order to maximize the OpenGL performance, Qt-Quick will try to detect which elements can be drawn together in one go, right? This works in practice by merging together the geometries of the elements which have the same state, let's put it that way, okay? So we can draw them all in one draw call. Sounds good? Okay. How can we know what's happening behind the scenes? Once more, Gamma Ray can tell us if we're doing good batching or bad batching. We have there are a few environment variables that you can set to understand that. but you can actually just launch Gamma Ray and ask Gamma Ray, please tell me how many different draw calls are being made in order to render this particular scene. And of course, the few draw calls we have, the fewer draw calls we have, the better. Okay, so let's actually do that. Let's play with this a little bit just to understand this point, or just to make my point even. Okay. So why does it say build? I don't know. Okay. Let me open a simple example. Okay, so what I have here is a simple grid full of rectangles. Okay, there are, I think, 6 rectangles in this small example that you can see over there. They're defined in a data-driven way. Okay, each one has a different color and a different width and height. If I run this, well, that appears on the screen. Okay, now the big question is, how many draw calls do you think this thing is rendered with? Yeah, that's what you would assume. There's different colors, therefore there must be 6 draw calls. Actually, no. Qt does better than that. That's 1 draw call for all 6 of them. Okay, Qt will merge the geometries of the rectangles, and since the rectangles are cleverly designed to use per vertex colors, that's actually drawn in 1 draw call. I can make sure that by running this thing inside the OpenGL tracer and seeing that it's just 1 call, but maybe I don't understand OpenGL or I don't want to learn OpenGL just to discuss this. So what I can do is also run this thing inside Gamma Ray. And it's this thing right here. Okay, so again, oh, sorry, where did it go? Here it is. So this is again Gamma Ray showing exactly the same thing. And what I can tell Gamma Ray is to visualize the batches. That is, how many different draw calls is this thing rendered with. Now, when I switch to batches mode, before I actually do that, the visualization here is going to switch to something which looks like that, but the semantics are completely different. So yeah, there we go. This particular visualization is going to show this. For each different color you see here, that's a separate draw call. Okay, so how many different colors do you see? Yeah, well, one for the background, yes, but all 6 of them are the same green, and it's the same green, trust me, I'm not cheating. Okay, so all of those are drawn in 1 draw call. Yep, that's great. Yeah, that's exactly what we wanted. Okay, so let's make our life slightly different, slightly more complicated, and let's change this example just a little bit. What's that? I don't know. Okay. Some comments in the source code. Okay, so let me complicate my life a little bit. What I have here is a very similar setup. The only difference now is that a few rectangles have a different opacity. So if I go over there, I see I've still got 6 rectangles, but 2 of them have opacity set to 1. One of them is 0.8, 1 0.75, 1 0.25, etc. Okay, now the opacity is changing a little bit for each rectangle. If I run this, okay, there's still 6 rectangles on the screen, but now the question becomes again, how many draw calls is this? Now the answer is no longer 1, unfortunately. I run this inside Gamma Ray once more. Where is it? Here, okay. And I attach to it. I go here, yeah. So now you can see a little bit more of a rainbow situation. Okay, these 2, the 2 in the middle, you see it's the same shade of orange. Those 2 got drawn together, but the other, they're drawn differently. Yep. So these ones are not batched together any longer. Why is that? Because I started applying a different opacity at each element. Okay, opacity is one of the countless things, to be honest, that will break your batching. Okay, if you have elements which have different opacity, the Qt renderer cannot draw them together in one go. So what it's going to do, it's going to split them, right? You need to draw these 2, which have the same opacity, the other 2, but then these and the other one need to go alone because they have a unique opacity and they must be drawn alone. Okay, so what is the moral story of this? The moral story is this, that Qt renderer uses a few simple heuristics to figure out what can be merged together. The reason why these are heuristics is First and foremost, because the things that can change is just too much. And second, we don't want this process to be more expensive than just drawing everything in the first place, okay? This process has to be reasonably cheap. So what it does, it just tries to go around and see, okay, all these things have the same material, the same opacity setting, the same clipping, and so on. And so they can be merged together. But it does not do some really crazy stuff that could be, in principle, be possible. It really does not do the optimal, because that's actually NP hard, so we cannot really go there. But it does a very good job. That's the point. The rule of thumb to understand from this is this, that every time my elements in my scene have a change in opacity or clipping or material, by material I mean the combination of shaders, textures, and uniforms, or render target, any change in these will cause a different batch to be generated, okay? So I must be careful about what happens, and also things like visual overlapping take a role. For instance, if you got two elements which are partially transparent, have the same opacity, and they don't overlap, then they can be drawn together. But if they do overlap, then I must draw them in order, and that means breaking the batching, right? Because you must draw the one behind and then the one partially opaque on top. So overlapping also and transformations take a role in this setup, okay? Now, I know what you're thinking, but wait a minute, is this a real problem, or now you're just making stuff up? Because some people believe this is completely made up. Yes, this is a real problem. I cannot give you any names because I work for my company, but I've seen so much code that tries to be clever, right, and produces awful results with hundreds in unnecessary draw calls. Okay, that's where we kind of close it up, in the sense that the simplicity of Qt Quick True, the fact that we can easily put together a complicated scene with very few little lines of code, is a double-edged sword when it comes to this, right? Okay, we're gonna give Qt Quick True to a designer. I don't know if there are any designers in the room, but yeah, sorry about that. We can give Qt Quick True to a designer, and they can come up with something very visually compelling, but perhaps disastrous when it comes to rendering. Then on desktop, everything works fine on your NVIDIA RTX Super Maxi GPU. Then you try this thing on a phone or embedded hardware and nothing works, and now we start with the blame game. Yeah, Qt Quick is terrible, Linux is terrible, actually no, Linux drivers are terrible. While there is some truth in that, you're not making their life any easy by submitting hundreds or thousands of draw calls, okay? So yeah, just to prove this, I'm not a designer, but did I make something like this? Yeah, can you make this one up? Okay, so there is this small demonstration here. Why is it not moving? This is supposed to move. What? Did I disable? Oh, yeah, that helps. Okay, so yeah, somebody came up. Okay, this conference, you have seen hundreds of car dashboards. Here's another one on the screen. Okay, so somebody made this nice, compelling graphic element. It's done hacked together very, very quickly, right? There is a needle that rotates on itself. There are a few numbers nicely displayed around it. You see there are these small notches all around it, okay? So how do I make this notch like this? Well, the designer just thought, let me put a rectangle, rotate it, and translate it over there, or something like that, okay? How do I make these numbers? Okay, again, take a text, rotate it, put it over there. But I think this thing is a bit too big and bleeds over, so let me apply clipping to all these notches. And there is somebody that decided it was a good idea. So let's analyze how many draw calls are made to draw this thing. So for the peace of mind, I'm going to disable the animation just to make it stand still, right? And again, start gamma ray, and it's here. And I visualize the batches. Now, yeah. And now that happens, right? Basically, each and every element by itself. Okay, this thing is drawn in the, I don't know, 100 draw calls for some reason. Okay, so our job, my job as a developer, is find out why is it like that. I mean, there is something wrong in the design. Okay, there is some slight opacity applied. Well, yes, there is. Some elements have 0.95 opacity that no human eye can possibly detect. Yet Qt Quick, of course, will say, oh, sorry, I cannot batch that thing together with something which has opacity of 1. Okay. Some other elements have clipping enabled, and there is actually a visualization for that. This visualization right here shows which are the clippers. Unfortunately, the contrast is very poor, so you can see there are some red areas, and those are the region of the elements that are clipping other elements, and clipping is one of the factors that breaks batching. So this thing is breaking batching. The individual markers, some of those you see there are two different colors because they put a slight background behind them and then something with opacity on top. So they need to be drawn in order, and this breaks batching. Yeah, over here is more or less visible that you see that. All these sort of small things that designer can just do, thinking this is just fine. And this single element is 100 draw calls, which again is fine on my machine. I tried this out on embedded hardware and it's terribly slow, right? And it's just one element in my UI. Then of course I got a speedometer next to it, which is another 100 draw calls, right? And then I got the current gear, added 1 million draw calls. And now the whole system is slow. The whole system does not keep 60 frames per second. Linux is terrible. Why am I using Qt? And so on. Yeah, that happens. Okay. So I'm kind of running time right now. So I want to thank you for your time today. If you have any questions, Lazaro is here with a microphone. So please wait for the microphone because otherwise I cannot hear you. Yeah, but meanwhile, thank you for listening.
Yeah, thank you. All right, who's first? Yeah, there.
Hi, thanks for the talk. I will have a question then from the designer perspective. It looks like in the last example for it's a lot of rectangles, a lot of colors. What will be the solution there? What if we will use an image? It will have a lot of alpha,
instance.
but then how does the alpha is being handled? How bad it is?
So in the last example, I mean, it could be that this was just a prototype, and then somebody thought, "Oh, look, this prototype looks cool. Ship it," right? Again, that happens. So a possible solution here could be, again, go in the code, figure out what's going on. Maybe there is some clipping which was completely unnecessary, some simply forgotten in the code, right? Maybe apply caching. You could cache the entire background when you think about it, right? Because it never changes. The things that change are the needle and this colored thing on the side. So apply caching, as we just saw at the beginning, to the entire background. And now it's one draw call for the entire background rather than I don't know how many. So use an image. So now that the design looks okay, we do the same in Illustrator or Photoshop or whatever, and then say, okay, that's my design, again, as an image. There are many, many trade-offs there. Okay? It just depends on how much time you want to throw at the problem. But there are for sure solutions, yes. So apply one of these, the one that you find more reasonable or the quickest or the one you like the most, and use that rather than, again, being too clever with the cute, quick programming on your scene, and then these things start to happen.
Okay, thanks.
You're welcome.
Hello, thanks for the talk. My question is about embedded here. Embedded OpenGL. Is there a difference in between how embedded OpenGL and desktop OpenGL might handle the number of draw calls? And if so, would there be a strategy to check the draw calls happening in an embedded device?
So in principle, there could be a difference, but as far as I know, Qt Quick does not actually do anything different or nothing significantly different between desktop OpenGL and OpenGL ES, in which case, in the case you add on the device. So since that's typically the case, what you can do is simply run your application inside an OpenGL tracer on your desktop, and then you know how many OpenGL calls you're doing also on the device. Vice versa, if you have an embedded device running Linux, you can just, again, compile something like API trace on the device itself, and then you can extract an OpenGL trace from the device and copy it over your computer, and then you analyze what Qt was doing exactly on your device. A long time ago, like 3 or 4 years ago, I added a couple of patches to Qt, because these days, at least on Linux, you can actually create an OpenGL ES context on desktop Linux. Okay, so if you set a couple of flags, I can show you some code later. You can actually create such a context on desktop, and now you'd have on desktop the same behavior that Qt Quick has on embedded devices. Okay, give or take. Okay, so all of this is definitely possible, but I don't expect any significant difference between OpenGL Desktop and OpenGL ES from the point of view of Qt Quick. Sure, there are some minor differences, but nothing really that could make a drastic difference in performance. Okay, all right.
Hey, thanks for the talk. Not a dumb designer here.
Okay, good.
So, like, from just from my understanding, so you said opacity breaks the batching. So if I have a case of I don't know, a pop-up window fading in, for example, like the designer wise, is there a spatial caching, so it can cache like a partial, like a part of a frame, and just do draw calls in the specific place where a pop-up fades in? And is it calculates, like, is it batches every element within this fading, within this pop-up window fading in?
So sorry. So the first part of your question was about caching.
Yes.
Okay. Do you want to cache the background or the pop-up itself?
Basically, when you have like, for example, like a list of elements, like a list view, and the pop-up does not cover or like the whole screen, just the bottom part. Is the top part caches, or is it still like redraws every element?
It's still redrawn every single time unless you cache it. The basic principle of any 3D graphics programming is that the first thing you do in a new frame is clear the screen. Okay. Yeah. So of course, again, take the advice about caching only after you have profiled and figured out, okay, this needs caching. In the general case, caching will be more expensive than just drawing it in the first place. So if you have a list view of elements, I'm expecting the drawing of each and every element not to be super expensive. So caching in that case really doesn't make any sense. If you need to cache, then you can cache the entire list view if you need something like that. You can cache the entire screen if you need something like that. But be aware of the price tag attached to that. Right now you're using a lot of memory that maybe you just don't need to use. What you really do there is analyze your painting inside an OpenGL profiler. And if that tells you, look, you are applying 12 different blurs for each element in your list, then perhaps it's now time to cache a little bit of that. Okay, but please be driven by the profiler. Don't just jump into, okay, let's optimize things. That never works. Okay, profile, find the bottleneck and solve the bottleneck, and then rinse and repeat the process until it's good. Okay.
All right, anything else? Maybe we have time for one more. So last question.
Otherwise, I'm around outside, so you can grab me. So please go ahead.
Hi, I've found that using a lot of text elements, separate ones, seem to create a lot of batches. Do you know of a way of handling that other than using layer enabled?
Well, the thing is, it shouldn't, because text elements themselves are going to use glyphs. So unless, like, for instance, they're all different fonts or something.
They should all be the same font.
Okay, that kind of surprises me. There must be something else in action. For instance, again, text is transparent, so it needs to be drawn in a certain order. But apart from that, the text itself should or could be drawn in one single batch, for the simple reason that the text itself can get the glyphs themselves go in the same texture, in the same atlas, if you want. And I believe that should already be handled automatically by Qt Quick. If it's not the case, then it's now time to fire up Gamma Ray, fire up an OpenGL profiler again, and figure out exactly what's happening. Because there could be something totally trivial, like opacity 0.99 applied to them. Something, or maybe inherited from some other element, and you don't even see that immediately, or something like that. By default, and Okay, I don't have time to prove it right now,
Okay.
but
No, cool.
if I put some text, random text on the screen, you will see that it's one batch. It will batch different text elements without problems.
Okay, thanks.
Okay, you're welcome.
All right, so that's
Oh,
it.
well, okay.
Thank you again.
There was,
I think-
there was one more in the back, but
Yeah, I think you could
okay, no,
take
okay.
that offline.
Yes,
so, yeah,
we'll take
after
offline.
this.
So again, thank you very much.